Hi, I'm Dan, and I'm presenting proof 18.2. So here, we're basically trying to show that the volume of a manifold is independent of the parametrization used. So we can start out by defining our parametrization gamma 1 over a parameter space U, and then gamma 2 over some parameter space V. We can say that gamma 1 is equal to gamma 2 composed with some arbitrary change of variables phi. So we have that the k-dimensional volume of our manifold is equal to the integral over the space V of the square root of the determinant of d gamma 2 of V transpose times d gamma 2 of V, and this is with respect to k variables in the space V. So now we're going to transform this to an integral over the space U using the arbitrary change of variables. V is phi of U. So now we have the k-dimensional volume of M is equal to the integral over U of, as we had before, the square root of the determinant of d gamma 2 of now phi of U transpose d gamma 2 phi of U. But now we have to note that we multiply by a scaling factor, which is the determinant of d phi, the determinant of d phi of U acting on dk of U, k variables in the space U. Now we must note that this d phi is just the scaling factor that we've used normally, for instance when we multiply by r when we're integrating in polar coordinates, and d phi is just a linear transformation that takes us from V to U. So we note that we want to express this all within the square root, so we're recollecting our terms a little bit, and we now have the determinant of d gamma 2 U T. And now basically we're noting that with our scaling factor determinant of d phi of U, we can re-express this as a square root of d gamma phi of U transpose times determinant of d gamma phi, because essentially the determinant of the transpose is equal to the determinant of the matrix. So expressing the determinant of d phi transpose times the determinant of d phi is basically just determinant squared of d phi, and because we're putting in the square root, we're fundamentally changing nothing about the problem. And again, we're integrating with respect to k variables in the space U. Okay, so now we have three determinants, and we know that the determinants are just numbers, so the order within the square root is fundamentally irrelevant. So basically it appears like a good idea to move the d phi of U transpose further to be the first in the list, which will be made more obvious as to why shortly. Then we'll write our d gamma 2 of phi of U times, oh, there's a transpose there, my apologies, and d gamma 2 phi of U, and then again we'll just have our d phi of U, and then dku. So we haven't changed anything, we've just moved some stuff around. But now we know, of course, by the proof 3.2 of last semester, and I believe proof 15.1 of this semester, that you can play around with the determinants And what you're basically doing is the determinant of matrices, determinant ABC is equal to determinant A times determinant B times determinant C. So basically what we're doing is we're collecting all of our determinants into one determinant. Like we have an expression with 3 determinants now. We're just basically saying that's the determinant of multiplying all 4 of our matrices together. And so now we basically have the determinant of d phi of u transpose d gamma 2 phi of u transpose d gamma 2 phi of u and d phi of u, once again with our dku being outside the square root sign. And now we have a very interesting expression, because we have our 2 matrices that are transposes, and it's d phi of u and d gamma 2 d phi of u. And if you remember from the chain rule, this is the same as the composition of gamma 2 and phi of u. So basically, we can rewrite this using the chain rule to say that we're integrating over u of the square root of the determinant of simply d gamma 2 composed with phi acting on u transpose times d gamma 2 acting on phi of u dku. And because we've already established up at the beginning of the proof that gamma 1 is equal to gamma 2 composed with phi, all we have left to say is that the k-dimensional volume is equal to the integral over u of the square root of determinant of d gamma 1 acting on u transpose d gamma 1 acting on u dku. So now, basically, we have an integral, we have an integral expressing the volume of our manifold with respect to a parametrization gamma 1 in the space u, which before we had the volume expresses the volume of the manifold with respect to our parametrization gamma 2 in the space v. We now have the same thing for u. We haven't fundamentally changed anything. We've made all legal transformations that preserve volume, and now we have an expression in another space. This means that the k-dimensional volume of our manifold is not related to the parametrization. It's independent of that, and now we're done. We've proved proof 18.2.